Hello all, welcome to the video lecture. In this video, we'll be discussing about the logistic regression. Well, logistic regression is a classification algorithm. As in linear regression, classification also aims to model the relationship between the independent variable and the dependent variables. However, the dependent variable in classification is the categorical data or the values that we want to predict takes on only a small number of discrete values. So classification aims to categorize which category an observation belongs to. So classification is a predictive modeling that works under the supervised learning setup. So as we also discussed previously that what is supervised learning and unsupervised learning, then classification is the predictive modeling that works under the supervised learning setup. So example of classification problems are like categorize the email into spam or not, detect online transactions as fraudulent or not, and detect tumor as malignant or the benign. So let's take the dependent variable or the output in this problem is y. For now, we'll focus only on the binary classification problem in which y can take only two values, which is 0 and 1 or 0 or 1. For instance, if we are trying to build a spam classifier for email, then xi may be some features of the piece of email and y may be 1 if it is a piece of spam mail and 0 otherwise. So given xi, the corresponding yi is also called the label for the training example. 0 is also called the negative class and 1 is the positive class, and they are sometimes also denoted by plus and minus, or 0 is denoted by minus and 1 is denoted by plus. And for binary classification, y is either 0 or 1 as we have discussed earlier. 0 means negative class or absence of something, and 1 means positive class, that means presence of something. For multi-class classification, the output variable y can have more than two values, that may be 0, 1, 2, 3 and so on. So the value of y may be 0, 1, 2, 3 and so on. So let's understand this with a simple example. So let's go for the classification problem in more detail. So let's suppose we are given a data set containing height and weight for a group of people, and our task is to predict the weight for new entries of the height column. And as we have earlier discussed, we can figure out this is a regression problem where we will build a linear regression model. We will train the model with the provided height and weight values, or we will model the relationship between the height and weight values. And once the model is trained, then we can predict the weight for the given unknown height. We can see here, like by having a best fit line, we can predict the unknown height values. Now suppose we have additional field which is obesity, and we have to classify or we have to categorize whether a person is obese or not depending on their provided weight. Now this is clearly a classification problem where we have to segregate the data set into two classes, that is obese or not obese, because the dependent variable here is a categorical that categorize whether the given data of the person is, like on the basis of data, given data, we have to categorize whether the person is obese or not. To solve this problem, let us first use a linear model, or let's first try with the linear regression model. On the plot, we can draw a line that separates the point into two groups, like with some threshold point 0.5, and all the data points below the threshold will be classified as 0, those who do not have the obesity. Similarly, all the observations above the threshold will be classified as 1, which means these people have obesity as shown in the figure. So It seems like this model has worked in this scenario. In the provided obesity classification, we can see linear regression does a reasonable job of assigning the data points into one of the two classes. But what if we had a single S with a very big weight, or we got a new data point on the extreme right of the plot, and once we have added this extra example, the regression line fitted to the data changes, and this would lead to classifying all the existing S's as a nodes. We can see here in the figure that the threshold point in the Westpred line has shifted to right as we classify everything right from this point as a 1 and to the left at this point as a 0, but by somehow adding one data outlier, the rightmost point would lead to classifying all existing ones as zeros, thus affecting the classification to the large extent. And another issue with the linear regression is that we know y is either 0 or 1, but the predicted values can be larger than 1 or less than 0. So for the classification, the dependent variable or the label may be either 0 or 1, and the predicted value can be greater than 1 or less than 0, like we can see here. So in this case also, in this scenario also, we cannot use the regression, or the regression cannot be the best choice for the classification of given data. So the logistic regression comes in. Let us try and build a new model which is known as the logistic regression, and we have here the linear regression. In linear regression, the equation of the Westpred line is given as here, which is defined by these two parameters w0 and w1x, and z is equal to w0 plus w1x. Now we want a function, this phi of z, that transforms the values between 0 and 1, and that is shown in the figure as we have the equation of this Westpred line z, which is nothing but equation of the straight line, and we want these values to constrain between 0 and 1, and the sigmoid function does what we want, and sigmoid function is given by this phi of z. This is the equation of the sigmoid function for any variable z, and which is nothing but 1 upon 1 plus negative exponent of this variable z. And we can see here this sigmoid function transforms the linear line into a curve. Here z represents the equation of a straight line as we have defined earlier. For us is the Westpred line from our linear regression, and this will constrain the values between 0 and 1, means the sigmoid function will constrain the values between 0 and 1. Now it doesn't matter how many new points we add to each extreme, it will not affect our model. So the other important aspect is for each observation, model will give us the continuous value between 0 and 1, and this continuous value is prediction probability of that data point, and if the prediction probability is near 1, then the data will be classified as 1, otherwise it will be 0. And it's also differentiable, like we can see here the sigmoid function of this phi of z is differentiable with respect to, once we differentiate with respect to z, we obtain the final result, which is equal to product of the original function, this phi z, and 1 minus the original function phi z. So it's differentiable with the simple derivative, and it is adaptable for the gradient descent. So basically we can see that the output of logistic function or the sigmoid function outputs the value between 0 and 1. So the logistic regression, instead of just predicting the class, It also gives the probability of the instance being that class, that is the probability of y given x. So it takes the probabilistic approach to learning discriminative functions. So let's see how the output of the model can be interpreted. First of all, let us summarize our model. We have the linear regression model defined by z is equal to w0 plus w1x. Then we have a sigmoid function which is phi of z. It will transform this linear model to the curve which is squashing in the range of 0 and 1. Now if we combine these two equations, we can write our model as yw of x, and which is nothing but the sigmoid function of the linear model that we have. So it is represented as yw of x. It is nothing but the output of our model. As mentioned earlier, instead of just predicting the class, the logistic regression gives us the probability of instance being that class. So for given data set where the level of the data set is 1 or y is equal to 1, we can say that output of the model yw of x is equal to estimated probability that y is equal to 1 on input x. Like if we are given with the two values of x, that is x0 and x1, which are x0 is 1 unit value and x1 is the weight of a person, and the predicted value is 0.7. Like with these two values we predict that the sigmoid function gives us 0.7. Then the output value tells us that the person has 70% chance of being obese. We assume this model output for the obesity classification problem that we have discussed before, and we can interpret the output in terms of probabilistic prediction of the true class. In other words, the YWX, which is our model output, it represents the estimated probability that level or output is equal to 1 for given input x, which can be written using the following notation. Here, that probability that y is equal to 1 given x parameters by w, this prediction value or our sigmoid function output or model output can be written as probability that y is equal to 1 given x, which is parameterized by w or our weight. Because the class can only take values 0 or 1, we can also write this in terms of probability that y is equal to 0 for a given input x, and we can write this as the probability of y is equal to 0, which is 1 minus probability of 1 given x, and which is parameterized by w. So for example, if the predicted probability is 0.85, then we can assert that there is an 85% probability that the output y is equal to 1 or the level is equal to 1, and 50% probability that y is equal to 0. This is useful as we can not only predict the class of an observation, but we can quantify the certainty of such predictions, and we will be more certain about the decision by using the decision boundary, and we will discussing about the decision boundary. As we can see that the output of sigmoid function is asymptotically bounded between 0 and 1, and when the probability of y being 1 is greater than 0.5, then we can predict y is equal to 1, else we predict y is equal to 0. And we will see When is it exactly that our sigmoid function is greater than 0.5? And if we look at the figure, we can see that the sigmoid function is greater than or equal to 0.5 when the value of z, which is nothing but the linear equation, which is the equation which represents the linear equation, is greater than or equal to 0. So if z is positive, then our model predicts y is equal to 1, and when the value of z is less than 0, then the model predicts y is equal to 0. So suppose we can see here, suppose we have this equation of z, which is z is equal to 6 minus x1. This represents a descent boundary, and any value of x1 which is greater than 6 will return a negative value of z, and any value that x1 is less than 6 will return the positive value of z. And once we get the value of z, then we can define our descent boundary by calculating the sigmoid value of this z. And once we get the sigmoid value, which ranges from 0 and 1, we can define our descent boundary as discussed before. So far we have discussed about the logistic function and the interpretation of output and the descent boundary. Now we will see how we will select the parameter, or how to choose the parameter, or how to feed our weight or W. Let's suppose we are given total m data points or training example, and each example has n features and one level or category, and the level is denoted by y, whose value is either 0 or 1, as we are considering the binary classification. As we have n features, each example will have n plus 1 length of column vector, and total m set of training examples with features and category or level y. With this given training example, we have to choose the parameters of fit, which is w, and we do by using the optimization of the loss function, or finding the minima of loss function, as we did in the linear regression. So let us see the loss function of linear regression first, and then we will go in more detail about the loss function of the logistic regression. For logistic regression, the loss function is mostly we use the mean squared error, and which represents the difference of actual output and the predicted output, and it is iterated over all data points, and then we do the square and take the average. It's for MSE, or mean squared error. Well, it is a convex function, and the loss function can be optimized easily using the gradient descent, because it is convex, and we use the gradient descent to optimize or to find our optimized weight value or the parameters, or we found the minima of the loss function using the gradient descent. And here from the equation we define the cost function as a square of difference between the y predicted and the y actual. We can see here we have got the y predicted and we have the y actual. Y predicted is represented by yw, or the model output, and yi is the actual output, and we take the square of difference for overall data points. Then what we do is, from this square we define the cost, and we redefine the loss function, which as the average of the cost function, and which is approximately the average of the individual cost over the training data for the linear regression. And this is the cost we want the algorithm or the learning algorithm to pay if the outcome, that is ywx, or the predicted value and the actual outcome or actual value is which is y are like these two values are far from each other, or we can say that cost will be high when the difference between the actual value and the predicted value is high, and the cost will be low if the difference between these two values, that is the actual value, actual output value, and the predicted value is low. So this cost function will define like how much they are near or far from each other. That means the predicted value and the real output value are near or far from each other. This will be defined by the cost function. And let us see here. On the left we can see the optimization of loss function, which looks convex, and as we discussed in our previous class as well, the optimization of loss function of the linear regression looks like this, which is convex in nature. Unfortunately, we can't use the same cost function, that is MSC, as we did for the linear regression, because as our prediction function is nonlinear due to sigmoid function or sigmoid transform, squaring this prediction as we do in MSC results in a non-convex function with many local minimums. We can see here, like if we perform the squaring of MSC result of the sigmoid function, then it will result in like this, and here we can see lots of local minimums. So if our cost function has many local minimums, then gradient descent may not find the optimal global minimum. As we can see here in the figure, there are two local minimas and one global minimum, and when we perform gradient descent, the gradient descent may get stopped at the local minimum instead of reaching the global minimum. So in order to solve this problem, the logistic regression comes with the new cost function. Intuitively, we want the loss function where the cost is smaller if the model's estimate is close to correct, or the output model estimate and the actual output is close to each other, and the loss function or the cost will be bigger if there is a big gap between the predicted output and the actual output. So we want to assign more punishment when the model is predicting 1 and the actual output is 0, and the predicted output is equal to 0 while the actual output is 1. So for this kind of loss function, we use the maximum likelihood estimator from the statistics, and we can obtain the following cost function, which produces a convex space friendly for the optimization, and this function is known as the binary cross entropy loss. And the binary entropy cross can be divided into two separate cost functions, one for the y is equal to 1 and another for y is equal to 0. So we can see here, for the cost function will be minus log of ywx if we are predicting y is equal to 1, and it will be minus log of 1 minus our model output or ywx when we are predicting y is equal to 0. Now let's suppose we are about to predict y is equal to 1, and we can see here the plot of the cost function versus our prediction. And if we plot the loss function versus the model estimate using the cost function separately, like the x-axis is what we predict and y-axis is the cost associated with that prediction, and for y is equal to 1, if the predicted value is exactly 1 or our model predicts exactly 1 and that's exactly correct, then the cost corresponds to 0, or it corresponds to the 0 cost. That is, the cost will be 0 when the prediction and the actual output is same. And if y is equal to 1, or the value to be predicted is equal to 1, and the model output goes to 0, then cost goes to infinity. So in this case we can see here, like, as the model output tends to 0 and the actual output to be predicted is, that is y is equal to 1, then we can see the cost goes to infinity. And for y is equal to 0, the cost, as we saw before, like the cost is evaluated as minus log of 1 minus yw of x, and it goes to plus infinity as the prediction goes to 1. And if the prediction is equal to 0 and our value to be predicted, that is y is equal to 0, then the cost will be 0. But if the value predicted is equal to 1 and the value to be predicted is equal to 0, then we can see here this value or the cost goes to infinity. So for the binary classification problems, y is always 0 or 1, or the level is always 0 or 1. So we can have simpler way to write the cost function. So rather than writing the cost function separately for two outputs or in two lines or two cases, we can compress them into a one equation and in more efficient way. And here is the equation of cost function in single line, and let us see how it is derived. Like we can see here, when y is equal to 1, then our equation is simplified to, here is our equation, and here if we substitute this y to be 1 in our original cost function, then the second part of this, or the expression in the right side of this equation, will be 0, and which leads to cost function to be minus log of ywx, which is what we had before when y is equal to 1. And when we put y is equal to 0, it will cancel out the first side of this original cost function's equation, and it will lead to the cost function to be minus log of 1 minus yw of x, and this is what we had before, y is equal to 0. So in this way we can express the cost function in a single line for two different cases, that is for output to be predicted is equal to 1 and output to be predicted is equal to 0, we can express in the single line of the equation. So the logistic cost function for the w parameters can be defined as follows. Here we can see the average of the cost function of m samples or m training sets, and as this function is convex, we choose this function while other cost functions exist. So after having this loss function, we have to fit the parameters w. So we have to find the parameters w which minimizes our loss function, that is j of w, or j of our parameter w. And now we need to figure out how to minimize the loss function, or we need to find the best parameters. And as before, we will use the gradient descent function. Here what we do is we repeatedly update the parameter using a learning rate. Here we start with some initial point of the parameter w, and we iterate till the convergence, and each iteration we compute the value of gradient of our loss function, that is the partial derivative of loss function with respect to the weight, and we update the value of weights to get the updated or new value of weight, and we take the steps in the opposite direction of the gradient, that we can see here that this step size is defined by this learning parameter eta, and the gradient of loss function with respect to the parameter w or weight w, and we keep on updating the value of weight until we reach the convergence, and convergence is reached when the gradient becomes 0. Now if we solve this gradient, or if we compute the gradient of this loss function with respect to our weight, we will get the partial derivative of the loss function same as that we found in the linear regression. So we can say that the gradient descent step in the logistic regression and the linear regression are identical, and only the difference here is the model output. Like in logistic regression, we represent the model in terms of sigmoid function, and in linear regression, the model is represented in terms of the linear equation. So it's all about the logistic regression. Once we obtain the optimized parameter values, then we can establish the relationship between the input and output. In another language, we can say that we have trained the model with the given input and the output value. Now once we train the model, we can predict the level when we get the new input values. So it's all about the logistic regression, and here we discussed about the binary classification using the logistic regression.